Again, our definition of standard enthalpy change of combustion, we've seen it already, but it's the enthalpy change when 1 mole of a compound is completely burnt or burnt completely in oxygen under standard conditions with reactions and products in standard states. Now, enthalpy change of combustion is complete combustion, but combustion can be complete or incomplete. So if you've been asked for the standard enthalpy change of combustion, it's complete combustion. Combustion itself can be both complete or incomplete. Complete combustion will occur in a plentiful supply of O2. This is actually technically GCSE stuff, and it's the same as GCSE. It's just the context might be a little bit harder. If you have complete combustion, what are the products? And I'm going to specify here, I'm talking about combustion of hydrocarbons, because of course you could just be combusting carbon or hydrogen. If I'm combusting hydrocarbons, I'm going to produce only, oops, let's go to blue, sorry, only carbon dioxide or water. So of course, if I'm only combusting carbon, I'm only going to produce carbon dioxide. And if I'm only combusting hydrogen, I'm only going to produce water. But if it's a hydrocarbon, I'm going to produce carbon dioxide and water for complete combustion. What about incomplete combustion? What's the difference and what are possible products? Incomplete combustion occurs when there is a limited supply of oxygen. That means you don't have as many oxygen atoms available to add to carbon and or hydrogen. Now, hydrogen is a little bit more reactive than carbon, and so does steal the oxygens first. So you do get water produced always, but our carbon may or may not pick up oxygens, and that means that we can produce carbon dioxide as normal, or carbon monoxide, or just particulate carbon. Particulate carbon, as in carbon solid, that's supposed to be an S. Carbon solid, i.e. soot. Carbon particulates cause a dirty flame, and actually we then see it as smoke. We can see the carbon particles disappearing off as smoke. That gives us or can cause respiratory issues. That's one of the reasons we don't like incomplete combustion, respiratory problems. So it can cause respiratory problems, particulate carbon. And what's the issue with carbon monoxide? Why don't we want to produce carbon monoxide? Because it's a toxic gas. It's a toxic gas. So wherever possible, we try to avoid incomplete combustion. To do that, we need to just have a plentiful supply of oxygen. Yeah, cool. Okay. The reason we've mentioned this is because they like to ask this sort of thing in an exam. If they ask you, or if they do tell you, no, they ask you to write an equation for incomplete combustion, there should be some sort of support, so information or something that you can use to work out whether or not you're producing carbon monoxide and or particulate carbon. If it's incomplete combustion, you can't just produce carbon dioxide and water. You must also or may also produce carbon monoxide and or particulate carbon. You might not even produce any carbon dioxide at all. So use the question to work out how you're supposed to know how much has been produced, and therefore how to write the balanced equation. They're not easy, but hopefully they should give you a bit of support. Okay, let's have a think about some calorimetry. So we can measure approximate enthalpy change of combustion using a calorimeter. I'm not going to go through this in loads of detail because there's loads to go through. I'm not going to go through this slowly because there's loads to go through, but you should be able to describe the equipment, or state the equipment needed to do a practical on combustion calorimetry, and write a brief method, so step-by-step method of how to calculate or how to do the practical for combustion calorimetry. So I'm just going to quickly label all of these equipment. So this is a thermometer. We have got a stirrer. We have got a boss and a clamp and a clamp stand. We have got our calorimeter or beaker, could just be a glass beaker, calorimeter. We've got our spirit burner. So usually we do combustion calorimetry with the first of the 4 alkanes, which are all do we? Is it 4? I can't remember if it's all 4. Anyway, whatever our spirit burner is, whatever it is that we're burning, we will put in our spirit burner, obviously, because we're burning it. And that's got our fuel in it, with or containing the fuel. We've got to have water. Oops, that looks like it's pointed to the thermometer. We've got to have water in our calorimeter. I think I've labelled everything. Oh, heatproof mat, you might want to label as well, just for safety. Heatproof mat. Have I labelled everything? Quick check. I think so. How do we do this then? What's the method? Method is we need to measure an amount of water into a calorimeter or beaker. We need to know how much water we've got. Not too much, not too little. 100 centimeters cubed is usually used. You don't have to, but not 100 centimeters cubed. You'll recognize it as 100 grams because we talk about the mass of water, but density of water is 1 gram per centimeter cubed, so it's 100 centimeters cubed. We need to then know how much fuel we started with, because we also need to know how much fuel we end with, and therefore how much we have burnt. So we weigh a spirit burner containing the fuel. We must measure the initial temperature of the water before anything is reacted, before the reaction starts. We then burn the spirit burner to heat the water, keeping as little space between the spirit burner and the water as possible. After there has been a reasonable temperature rise, around 30 degrees-ish, we then stop heating and record the temperature again. So we record the final temperature, the highest temperature, reached. So once there's been a reasonable temperature rise, we record the final temperature, the highest temperature that was reached. And then we need to reweigh the spirit burner. So we need to have, at the end of this, a mass of water, a temperature change, and we need to know the mass of fuel that was burnt during that time. And we can use Q equals mc delta T to work out the heat energy transfer. Ideally, the calorimeter should be isolated from the surroundings so that only the water absorbs the heat given out by the fuel. Of course, that can't always happen. And actually, one of the things they like to ask us about, and which we'll go on to in a second, is how to make reactions better, how to make them more accurate, and how to have less heat given off to the surroundings. So experimental values for the enthalpy of combustion are usually less exothermic. They're less exothermic, so they're less negative. That means that it looks like less heat has been given out during the reaction. So that's when we do it experimentally in a laboratory or in school, when we actually do it, compared to data booklets. But data books are used during ideal conditions, and they're used during they are found using Hess's law. So it's not an experimental value when you look at a data book value, it's a calculated value using Hess's law. So the values are going to be different. So what are the main contributors to this difference? There's quite a few, so I'll go through them nice and speedily. Heat loss due to surroundings from the spirit burner, the wick, and the calorimeter. Fuel loss from the wick and the burner. From evaporation, Evaporation. So the fuels tend to be quite, what's the word? Volatile. That means they turn into the gas state easily at room temperature. So that means they evaporate easily. So we could get fuel loss from the wick and from the burner, which would mean that our mass of the fuel that has burnt looks bigger than it actually was. So that can cause issues. There could be water loss by evaporation. So as water at in any temperature will evaporate eventually. We know that puddles evaporate. So water at any temperature will evaporate, especially if you're going to heat it. So it might evaporate more. So you might get water loss. If you get water loss, the actual water you're going to be measuring the amount is going to be smaller, which may mean that the temperature you see is actually greater than it should be, but also you get energy loss with evaporation as well. So they kind of counteract each other a little bit, to be fair. But there is an issue. It does mean that the experimental values are different to databook values. We also might get incomplete combustion, which is not going to have the same enthalpy change as complete combustion. And we could see that we'd see soot on the bottom of the calorimeter. There's also going to be heat that's used to raise the temperature of the calorimeter itself. So when you heat the water might also heat the calorimeter as well. So you're going to lose temperature of water, lose heat from the water that way as well. Or you won't, the heat won't be transferred to the water, it'll be transferred to the calorimeter. And we might not have the reaction occurring under standard conditions either. So maybe our temperature is a little higher or lower than it should be. That is also going to contribute to the databook value being different to the experimental value. Oops.